I didn't know how popular this topic is until recently, but this is a very, very, very popular topic. It's not the world's most popular topic at Swansea University, but globally it's huge. It's on a global scale, it's very, very popular. And I didn't know that until a few years ago, actually. Any Dilbert fans? Okay, so let's talk about the next exciting part of the lecture, or the volume visualization material, which is marching cubes and marching squares and isosurfaces and isocontours, which all sound, I think these are the key words. I'm not sure, but in the description of the module, there's like a list of topics discussed and all that stuff. And I think these are the terms that scare some of the students away. That's my theory. I'm not sure. They see those topics, those list of topics, and they're like, "Oh, I'm dropping this. I don't like those words." I could be wrong. So before we talk about an algorithm for extracting isocontours and an algorithm for extracting isosurfaces, we need to introduce the terminology, what they are. An isosurface is a surface representing a constant valued scalar function. So what does that mean in English? So an isosurface is a surface that is the same value at every point on the surface. So it represents a constant value. That's what an isosurface is. And we've seen isosurfaces already in the slides. I might not have called them isosurfaces, but we have seen them. So you can, you can input a CT volume data set and then generate a surface that represents the skin. The skin has a constant scalar value, has a constant density. It represents, you can represent the skin with an isosurface. Same with the surface of the bones or special soft tissue. We're going to see more examples as we go through. Don't panic if it doesn't sink in immediately. I remember learning this myself and hearing the term for the first time and hearing the professor try to say what it was and not understanding the first time. Oops, I didn't hear it. So don't panic if it doesn't make sense the very first time. That means I lose my screen capture again. Let me just try something.
You stop it and start a new one.
Yeah, I'm going to try that. So I guess this one's going to crash. It's exciting, isn't it? The suspense. Ah, it didn't crash. Okay, that's interesting. So let's try then.
Yeah, I think it's because you stopped recording before the track was switched on.
Maybe. Can everybody see that? Okay. Good. Hopefully I'll trip over the cord a few more times, add some more excitement. So an iso value is the scalar value used to generate an isosurface. It is the value that that surface represents. Right? If you can imagine sliding a person into a CT scanner or an MRI scanner and that machine sampling the density of the volume at regular spatial units, every sample is going to have a density. Right? It's a density. So there'll be one density that corresponds for different tissues, like one for the skin, one density for the bones, another density for the teeth, different densities for the soft tissue, and so on. Right? And you can use those density values as iso values to generate isosurfaces. It's a little bit abstract right now, just using natural language. That's one of the great things about visualization is as soon as you see pictures of these things, then it all makes sense. And hopefully the hammering will keep going and get louder and louder each time. Should we knock on the door? If I had a hammer, I could knock on the door and back at them. Okay, so those are two very important terms, and we've already seen isosurfaces, right? Here are some isosurfaces, one representing the skin, another representing the surface of the bones, representing soft tissue, and so on. And if we go back to the volume visualization pipeline, this is what we're traversing. The different stages. So we start with sample data. We represent it using a set of boxes or cells. Then we perform a surface extraction technique, which is what this lecture is about. We end up, here we have boxes, here we end up with triangles. A set of triangles, and then we project the surface from 3D space to 2D space. And we end up with that image. This is multiple isosurfaces, by the way. It's not just one. It's multiple isosurfaces. So that is conceptually what we're talking about. And they are so-called indirect representation of the data. In other words, you don't see the data directly, you see interpolations, you see interpolated data, and that will make more sense once you've seen what the steps are. So isosurfaces are based on the iso values, and so that means choosing an iso value that is meaningful is a very important part of generating an isosurface. But they are very interesting, generally speaking, because they represent boundaries. And boundaries are usually the most interesting subsets of any volume data. Right? A boundary, right? There's a boundary between the air surrounding me and the inside of my flesh. Right? It's the skin. That's an interesting boundary for lots of reasons, right? Otherwise I'd be dead. That's one interesting reason, but if, boundaries just in general represent, generally speaking, the most interesting subsets of volume data. When we look around, you're looking at boundaries. That's part of the problem with people, is they only see the boundaries. But when you look around, you're only seeing the boundaries. You're generally not paying attention to anything in between the boundaries. Right? So that's one of the, that's one of the consequences of isosurfaces, is it focuses on boundaries, and boundaries are generally very interesting. But which boundary you see depends on the iso value you choose. And here are some more examples, by the way, of isosurfaces. And we're going to talk about the algorithm that generates isosurfaces. So how is it possible to take a 3D set of volume data as input and as output generate an isosurface? How is that possible? That's what the Marching Cubes algorithm does. And it's a little bit complicated. There are some complicated steps in there. So before we jump into the complicated 3D version of the algorithm, we're just going to have a look at the 2D version that operates in image space only, and it's called Marching Squares. The equivalent of an isosurface in a 2D plane is an isocontour. I think we did mention isocontours already, didn't we? Anybody? What's that? 2 slides ago. Yes. Where do you see isocontours in your daily existence? Your exciting daily existence? You've all seen isocontours many, many, many times in your life already. And some of you see them on a daily basis. Anybody have any ideas where you see them already?
Screens.
Screens? Yeah, you need a screen. They're associated with data, a special kind of data. When you're looking at the weather reports, right? You look at the weather, right? It's raining. Has anybody ever watched the weather report before? So if you turn on the weather report, you usually get a map of the UK with clouds. But there are also isocontours oftentimes, if it's a good weather report, on the map. And the isocontours are typically showing temperature and pressure. So if it's showing temperature, it means that every value along the contour is the same temperature. So it's going to be, like in the UK, typically 5 degrees, the 5 degree Celsius contour lines. So there'll be, the regions of temperature will be separated by isocontours in a typical weather forecast. Same, the other typical weather variants that weather reports focus on, well, wind direction is one, but pressure, air pressure, barometric air pressure. High pressure corresponds to good weather. Low pressure corresponds to bad weather, rain. Everybody familiar with that? Everybody knows that already, I guess, from watching.
Geographical maps without.
Very good, Carlo, very good. Yep, it's... So if you see a high, sometimes the weather forecaster will, in other countries, not the UK, but in other countries, they might say we have a high pressure front, coming from the west. That means, yay, it's going to be good, a warm, sunny day. It's coming. But in the UK, you'll see we have a low pressure front surrounding the islands. Anyways, I'm getting carried away, but you see them every day in the weather report. Now you know what they are and how to interpret them. Although they don't use the terms isocontour in the weather report, they just show an image and you see lines surrounding regions sometimes. Humidity is another variant, isocontours of humidity. And as Carlo pointed out very rightly, another common place is on maps. And isocontours are used to show the curves of constant height. Like every location on an isocontour on a map is usually, it could be the same height. I think that's the topography or something. Yeah, topographic map. That's what we're looking at right now. Isocontours And the question is, how do you generate an isocontour? How can you compute an isocontour if you input a set of 2D scalar values and you want to generate on the other side an isocontour? And that's what I'm going to try to describe right here. This is a 2D grid of sample data. The data values are stored at the intersections of the grid. Right? So there's a 6 and so on. And then edges are drawn between the samples that represent two-dimensional sets in 2D space, right, to cover the whole space. So how could we imagine generating an isocontour from this 2D set of samples? This is a set of 2D samples, by the way, and this is an isocontour. And one thing to just notice before we talk about the algorithm is this is a boundary, and on one side of the boundary, all the values are below 4, and on the other side of the boundary, all the values are above. I'm sorry, it's the other way around. All the values on this side are below 4, and all the values on this side are above 4. So it's a boundary that separates the values into two categories. So how could we actually generate it? We can start with the top left cell, or square, or whatever you want to call it. And then for every cell, we examine the 4 data samples and we make a decision. We look at 3 and we say, okay, is 3 above the ISO value or below the ISO value? In this case, it's below. So we put a little indicator that says it's below. And then we look at the next 3 and say, is it above or below? And we say it's below. So we mark it as below. Then we look at 3 and 6. Then we look at 6 and we mark it as above. Right? 6 is above the ISO value. And then we notice, okay, if 6 is above the ISO value and 3 is below the ISO value, it means the isocontour must pass through. It has to pass through those two. It must intersect the edge that connects 6 and 3 together. Right? If we want to go from 3 to 6, we have to pass through the value of 4. Right? You can't get to the value of 6 from 3 without passing through 4. So we mark this as an intersection. The isocontour must intersect this edge. And where does it intersect the edge? We use interpolation to find out where the 4 is on this edge. Right? So the 3, 4, 5, 6, it's about a little bit towards the 3. It's almost halfway. Right? Then we move on to the 5. It's above the ISO value, so we know that it doesn't intersect this edge because 5 and 6 are both above the ISO value. So there's no edge intersection there. 3 and 3 are both both below the ISO value. So there's no intersection there either. And then the last edge is 3 and 5. So 3 and 5 span the isocontour. Right? They're on opposite sides. One's below and one's above 4. So we know that the isocontour must intersect that edge because it spans the value of 4. So 4 is above 3 and it's below 5, therefore it intersects this edge. So we have 2 intersection points. This intersection point happens to be exactly halfway, right? Using interpolation, we know that this one is exactly halfway between 3 and 5. We have 2 intersection points in that square, and then we just take the intersection points and join them by an edge. And we have one edge of our isocontour. Did that make any sense? I hope. Did I lose everybody there? Should I do another? And you do that same process for every square along in the grid. I'll do it again on another square. Maybe I should do it on one that I can reach. For example, typically you traverse the squares from top to bottom, left to right. You just march through the squares. That's why it's called marching squares. So you march through the squares, you look at you examine each corner, find out if it's above or below the ISO value, and then compute the intersection points. I'll pick another square and explain it again, like this one. Because it doesn't matter. Usually the squares are traversed in order, but to explain the algorithm, I can just pick any square because it works on a square by square basis. I look at this data sample and I decide, okay, this is above the ISO value, and then I look at the next one. It's below the ISO value. Therefore, the value of 4 comes in between these two, and the ISO contour must intersect this edge. So I have 2 data samples that span the ISO value, and then I compute the intersection point with interpolation. Right? It's more towards the 3, the weighted average. Right? I look at these two, then I look at these two, I notice that they're both below the ISO contour value. So I know there's no intersection. There's no 4 to be found along this edge. I look at the next edge. The first one is below and the second one is above. So there is an intersection along this edge of the ISO contour with that edge as we're spanning. It's 4 again. I use linear interpolation to find the position of the intersection. And then I go to the next edge, 6 and 6. But they're both above the ISO value, so there's no intersection. Audrey?
Could you make speed it up by using bigger squares initially and then do resolution?
Yes, definitely. Yes. So as Rodri very astutely pointed out, that's a good observation. The results are going to depend on the size of those squares. That is, another way of saying that is the results are going to depend on the resolution of your data. And you can accelerate it. The other thing to notice is that there are lots of empty squares. So you like this one, you just see, okay, all 4 are above the ISO value, so just skip it. Just move on. Carlo?
The line only, this might be silly, but the line only crosses 2 edges with square tops, right? So once you cross 2 edges, can you just not bother checking the others? Because I can't think of a situation where you could cross 3.
I have to think about that, actually. I believe that is correct. I can't be not 100% sure about that. I have to think about that.
I just thought about it. You can, on the right where you have 3, 3, 3, 2. So if it was 6, 3, 6, I don't know, I have to show it, but anyway, you can cross actually all the lines.
I think you're right, Colin, actually. I think you can only, in this particular example, I think you can only have 2 edge intersections. I don't think you can have more than 2 edge intersections. Yeah, you think you can have more? Describe a cell where you could have more, the numbers.
So move right.
So this one would
No,
be,
move right.
like this
so,
one?
Yeah. So imagine where you're holding your finger, move left. Imagine this is 6.
Okay.
Right? So it would cross that, right?
So if this is a 6, we have an intersection
And
here
this one,
and here.
yeah, so this is 6 and above is 3. So
This
line,
one's 3.
no. The 3 is 3 above, where you're rolling
Yep,
a 6, right?
Yep.
Okay.
That's 6.
So, yeah. So that means the line would cross through.
Yep, it crosses here.
It crosses here, then goes up because that 2 is, for example, also 6.
So if this was a 6,
Yes.
and this was a 6.
Yes. So it would cross through these 2, and then above that 3 would also be a 6.
So if this was a 6 and this was a 6,
So you can go
then
with
you'd
this.
have, okay, yeah,
3,
those 2
and
and
above that
those
3
2.
is also 6.
Yeah. Wait a second, 6, so 6. Yeah, I think you're right. Yeah, then in that case you'd have 4 intersections. Yeah. Yeah. So everybody understands the 2D version of the algorithm? Maybe? But if you don't have to panic, because you can find this explanation online or just read it in a book or read it in a paper. And back to Rodri's observation, we could have a multi-resolution representation where we have a low-resolution grid on top that describes the child grid nodes and skip over big portions. But it is definitely, the results are definitely tied to the resolution of the data, how big the squares are. I think one thing that is related to what you said, Carl, is you can never have more than one intersection along the same edge in this particular algorithm. Like you couldn't have 2 intersections along the same edge between two samples. And that is a limitation of your data resolution. So if you wanted to have 2 intersections, like imagine a surface that comes in and then exits. That's possible, but that's not going to get picked up by this resolution. If I want to pick up a high resolution surface that passes through like this twice, I need to subdivide the cube, split it up into 4 to catch that, so to speak. So you can only have one intersection on an edge, on one edge in this algorithm. Okay, so how does that work in 3D? Oh, I guess we should stop then. It's 3 o'clock. So we're going to talk about the 3D version of this algorithm on Monday, which is very exciting, by the way. Very exciting. Any questions? Happy Friday and have a good weekend. I'm so disappointed that the hammering stopped.